In the paper Cryptographic Limitations on Learning Boolean Formulae and Finite Automata, Kearns and Valiant presented work connecting learning to cryptography. Specifically, they showed that pack learning the following classes of functions is intractable, in other words hard, for the following cases. Number 1, polynomial-sized Boolean formulae, which is the class of Boolean formula on n Boolean inputs whose size is polynomial. Number 2, acyclic deterministic finite automata, which is the class of deterministic finite automata of size at most polynomial that accepts only strings of length n. And finally 3, constant depth threshold circuits, also known as neural networks, which is for some fixed constant natural number d, the class of threshold circuits over n variables with depth at most d and size at most polynomial.
Let's introduce a few important concepts and definitions from the paper. First, representation-independent hardness states that learning is difficult regardless of the form which a learning algorithm represents its hypothesis. The paper proves representation-independent hardness for the above three classes of functions, which have important implications that we'll go over later on.
Distribution-free learning is repeatedly brought up in this paper as the framework for many of the future conclusions. It is built off of the pack learning framework previously explained in Theory of the Learnable, but makes the important statement that we make no assumptions about the distribution D we are sampling from. The implication of this statement is that the learning models developed for one task can easily be applied to another task with the same input-output types. This framework of learning is also sometimes referenced as strong learnability. On the other hand, weak learnability would operate under the same framework without a high bar on the resulting accuracy of the learned representation. We can think about learnability as some small benefit over random guessing that comes from an ability to detect the small bias separating examples. This benefit decreases as the complexity of the problem grows larger.
A key takeaway is that our algorithm doesn't need to learn the specific distribution, but instead we want to operate well in that distribution. An analogy to better understand this is the way that we interact with gravity. In our everyday actions, we don't really worry about the mechanics of physics every time we take a step or pick up a laptop. We just need to know the actions that will lead to the outcome we want. In the physical world, we as humans learn how to do this through trial and error and seeing examples from other people.
The last definition is proper versus improper learning. For proper learning, you need to solve NP-complete problems. For improper learning, it's basically just pack learning, and it's easy to do with certain distributions. The majority of this paper is spent defining various terms for learnability and cryptographic systems. Then, various proofs of hardness are presented for each class of functions.
These are the main takeaways of this paper. First, this paper was the first to show hardness of learnability. Second, it extended earlier work on learnability to nuances with weak and distribution-free learning and had the vision to link learnability with cryptography. Third, it reduced cracking well-known public key cryptosystems, such as RSA, to learning. This means that if P equals NP, then everything can be learned in polynomial time. Conversely, it means that if learning can be done in polynomial time, all of our cryptographic security schemes will be broken. 4. It ended with the open problem of proving representation-independent hardness for even simpler classes of formulae and circuits. Finally, this paper extended the ideas by Angluin and Karatanov to prove hardness for learning with queries. Karatanov's paper determined trade-offs between running time and the number of samples necessary to learn. It also extended hardness to all non-trivial distributions.
Well, so the driving idea of my learning paper is that probably most things are hard to learn because we don't find it so easy to learn. So it must be that what we can learn is a very constrained class of problems. But of course, if I can learn something, so can you. And then trying to understand the limits, what are hard to learn, then in fact I got this kind of things which cryptography people were looking at. So it was a kind of a logical bridge to make, inevitable bridge to make. Of trying to find what's easy and then what's hard. The evidence you can get for something hard to learn is exactly what cryptographic functions look like. Yeah, well, this is like if you write a kind of a first paper in something, it's hard to even. You don't know what it's not that you had a list of challenges to write down. You just didn't know what to do. So so we had no idea what direction to go in. So I read some books on what people thought about reasoning and learning, reasoning and inference. So I think it's in that case it's very hard to, since I didn't know which direction I was going in. It's particularly hard to give you a good answer. What challenges I faced. So somehow the idea emerged somehow from. Then I recognized it. So maybe it's a good idea.
How about in some of your later work?
Well, in kind of things where you're trying to prove a theorem. Then it's much clearer what you can probably reconstruct more easily, what you've done. So there's a theorem, then you try to look at the three theorems that are maybe closest, you think may help, try to understand that, and then you figure out, this argument is interesting. So there I think it's easier to reconstruct one's thought processes. And presumably in experimental work, I presume it's similar that,